We're going to look at some more volumes of revolution to review, and then we're going to do a new volumes strategy, finding volumes of known cross sections. So first we have an A, B, and C here. We're going to set up our integral but not actually work it out. We're going to find the volume of a solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1. First about the line y equals 1. So the region we're talking about, here's our 2 minus x squared parabola, and then this is the line right here. This is also in part A our line of revolution. So if we look at a representative rectangle, it's going to be touching, that is the line of revolution will touch our region all the way through. So that's going to make our delta volume, the volume of this rectangle that we're going to revolve about the line y equals 1. If we pull that out, it's going to look like a little slice like this. It's going to be a mini disc, a very short cylinder. And so that delta volume is going to be the area of the cross-sectional piece, which is pi r squared, times that thickness, that height, which is going to be delta x. So this is our disk method. So the radius for us is going to be this distance from the axis of revolution to that curve, or we can think of that as being top curve minus bottom curve. So that is going to be our top curve, 2 minus x squared, minus the bottom curve, 1, and then times a delta x. So that's going to make that be pi times 1 minus x squared delta x. So our volume will then become the integral. We add all those slices up. We can pull the pi outside. We need to know where do these curves intersect. What are our limits of integration going to be? So to do that, we can take 2 minus x squared and set it equal to 1. And if I subtract the 1 and add the x squared, and then take the square root of both sides, we'll see that's going to go from negative 1 to 1. And then we're going to get our 1 minus x squared dx. And we're just going to leave it right there. That's going to be our volume. Now, if we revolve this around the x-axis, then this is going to look a little different. So we still are going to have our rectangle that's going to look something like this. But now as we revolve it around the x-axis, you can see that there's going to be this gap. So if I take that slice out and turn it on its side, it's going to be what we are going to call a washer. So our washer, our delta volume, is going to be that area of that cross-sectional piece right there, which is going to be pi times the outside radius squared minus the inside radius squared times then the delta x. So the hard part is figuring out what these things are. So the outside radius is going to be that distance from the edge of our solid to the axis of revolution. And since that's vertical, we're going to go the top curve, which is our parabola, 2 minus x squared, minus the bottom curve, which is just 0. That's the x-axis. And then that's going to be squared, minus the inside radius, which is going to be the distance from our axis of revolution to the hole. So that inside radius is again going to be vertical. That's going to be the top curve, which is R1, minus the bottom curve, the x-axis is 0, and then that's going to get squared. So our volume is going to be pi. We're going to go from negative 1 to 1 again, and we're going to just write that as 2 minus x squared squared, and then I guess we can just say that's minus 1 squared, which is 1 dx. Now if we do the line y equals 4, that line is going to be up here. So here's approximately our line y equals 4. So now when we take our rectangle and we can look at this rectangle again right here, and we spin it around, whoops, when we spin it, I kind of lost my rectangle there. When we spin that around that line y equals 4, we're going to get that big washer. That is, we're going to get something that's got that pretty good sized hole in it. But it's still going to be a washer, so it's going to look something like that. So that delta volume is still going to be pi times our outside radius squared minus the inside radius squared times a delta x. Now the outside radius is slightly different because now we're going to go from the axis of revolution to the edge of our solid, which is going to be this distance right here. So this is our outside radius, but that's always staying the same. That's going to be that 4, the top curve, minus the 1, the bottom curve, squared. That's going to be our outside radius squared, minus our inside radius, which is going to be that distance from the axis of revolution to the edge of our hole. And so that distance right there is our inside radius, and that's going to be the top curve, which in this case is just the line 4, minus the bottom curve, which is our parabola, 2 minus x squared. And that inside radius is going to get squared. So our delta volume is going to look like pi. The 4 minus 1 is 3. 3 squared is just 9. And now we're going to get minus, and then if we distribute that negative sign, 4 minus 2 is going to be 2. The minus negative is going to make that a plus x squared squared delta x, making our volume that integral from negative 1 to 1, pi times that integral, and we're going to get the 9 minus 2 plus x squared quantity squared dx. So let's look at a new idea. We're going to talk about volumes of known cross sections. So we are going to find the volume of the solid where the base is bounded by y equals 0 and y equals 3x minus x squared. So we can see the parabola drawn there, and y equals 0 is going to be just the x-axis. So that's just going to be this line right here. So the region we're talking about is this one that's going to be right here sharing the x-axis. Now we're going to take cross sections perpendicular to the x-axis that are a variety of different shapes. So I'm going to start with semicircles. Now this is kind of hard to imagine. I've got some good visual aids in class. So if we take our rectangle right here, then we're going to imagine in part A that we're going to get some semicircles that are coming out from the board here. So if you were to lay your head down on this iPad and look sideways, what you would see, I'm going to pull that out, is going to be a semicircle that's coming right out of the iPad. So it's going to look something like this. This is my best approximation to what that's going to look like. Again, this is what you're going to see when you have your head down on the actual iPad here. Now the delta volume is always going to be the area of that cross-sectional piece, in this case the semicircle, times delta x. So what that area is will vary from one solid to another, from one cross-section to the other. In the case of our first one, semicircles, that's going to be 1/2 pi r squared. That's going to be the area times a delta x. So our radius, if you notice that right here, this length right here is this distance right here, which is our function. That's going to be the 3x minus x squared, but that's a diameter. So the radius is going to be our function 3x minus x squared divided by 2. So that's that's going to make our area 1/2 pi r squared. I'm going to combine the 1/2 and the pi and call that pi over 2 times, and then our radius is going to be this 3x minus x squared over 2 squared times our delta x. So I'm going to slide that up a little bit. So what we get then is going to be the pi over 2, but when we square our radius, we're going to get that 3x minus x squared squared. The 2 in the denominator is going to get squared and become a 1/4, making this pi over 8 times the 3x minus x squared squared delta x. That's our delta volume. So our actual volume, we can pull that constant out, and we're going to integrate. We can see that this 3x minus x squared, we can see where it crosses the x-axis. If we factor that common factor of x out, that is going to intersect at 0 and 3. So our limits on the integral are going to be 0 to 3, and our integrand is going to be this 3x minus x squared squared dx. So there is going to be our first one. This is our semicircles. Now don't try to memorize these, just try to recreate them each time. Okay, I'm going to see if I can take this off as we did it all down below. Now the next one we're going to look at are equilateral triangles. So I think these are the hardest. So now, I don't know if I can let me see if I can take out no, let me try again here. I'll try to remove our semicircle, and now I'm going to try to draw, here's our rectangle now, and what's going to come out here is going to be an equilateral triangle. So again, that's coming out from the paper or the board, and if you lay your head down on the board and look, you're going to see an equilateral triangle that has a little bit of thickness to it. So that's our delta x thickness, something like that. So our delta volume is always, again, going to be the area of the cross-sectional piece times delta x. So the area is going to be our triangle, which is going to be 1/2 base times height, delta x. Now, let's look some more at this equilateral triangle. Now we know this distance right here is our function. That's this distance here. That is our 3x minus x squared. But when we drop the perpendicular down here, this equilateral triangle, which is also equiangular, becomes a 30, 60, 90. So we know that the side lengths in a 30, 60, 90, or we used to know, are going to be x. Now remember, that's our short leg here. 2x is our hypotenuse. That's not really very important to us, but this distance is what we're really after. The height is going to be x times the square root of 3. So, see if you can follow this now. I'm going to redraw this out here for a moment. So this is what we're calling x, and this is our x squared of 3. But our x is going to be 3x minus x squared divided by 2. See that? That's going to make this height be the square root of 3 over 2 times 3x minus x squared. That is the height of our green equilateral triangle. So our delta volume is going to be, here's our area, 1/2. The base is our whole 3x minus x squared times our height, which is the square root of 3 over 2 times 3x minus x squared. And then we've got that delta x tacked on the end. So our two constants are going to get together and be a square root of 3 over 4. These are really the same thing. So when they multiply, that we can write as 3x minus x squared times delta x. And that is going to make our volume for this equilateral triangle. The constant we pull out is going to be square root of 3 over 4. We're still going from 0 to 3 for limits. And again, we get that same integrand, 3x minus x squared dx. Notice the only difference there is that constant in front. And that's what changes from the different shapes, the different cross sections. Now we're going to do a quarter circle. So imagine now that we are going to see if I can erase this again strategically. I'm going to try to take that out of there. So now when we look at our little rectangle, what's going to come out of there is supposed to look like a quarter circle. I'm going to draw it over here. So there is a quarter circle with a little bit of thickness. So you can imagine it's got just a little bit of thickness. Now we know again that a delta volume is going to be the area of the cross-sectional piece times delta x. So since this is a quarter circle, that's going to be 1/4 pi r squared is going to be our area times a delta x. Now this is actually easier than our semicircle, I think, because now this is not the diameter. Remember, that's this distance right over here. That distance is here. That is our function right there. That is the radius of that circle. And so our delta volume is going to look like, if we put the 1/4 and the pi together, that's pi over 4 times the radius, which is our function, in this case 3x minus x squared times delta x. So our volume, we go to an integral, and again we're going from 0 to 3. We pull the constant pi over 4 this time, and what's left is, once again, our function squared. So notice the similarities, notice the differences. So far in our 3 different cross-sectional pieces, we've got different constants in front, but the same limits and the same integrand. All of these so far have been 3x minus x squared quantity squared. Okay, let's see, we got red now. Now we have, what we're saying here is a right triangle with the leg on the paper. And let's see what that might look like. Let me see if I can erase this. So we're going to imagine now that we're going to, here's our rectangle. I'm going to make it red. There's the rectangle. Now coming straight out from the paper, this is going to be perpendicular right here, and we're going to get our right triangle so that the leg is what's going to lay on the iPad, my iPad, or your paper. So I'm going to redraw that over here. So we're going to get this right triangle, and it's going to be, oh, and I should have said, I'm going to doctor this up now. I'm going to say it's an isosceles, right triangle. So that means these two side lengths are going to be the same. So we know that our delta volume is going to be our area of the cross-sectional piece times delta x. The area of our triangle is going to be 1/2 base times height. So since our right triangle has this base right there on the iPad or your paper, that is just our function. So we're going to get 1/2 times our function, which is at 3x minus x squared, times the height. But since this is isosceles, then these two side lengths are the same. So that's going to be another 3x minus x squared, and then our delta x. So our delta volume is going to be 1/2, and here again we're seeing our function squared, delta x, making our volume the constant that comes out on this one is just 1/2, and I don't know where I got those limits from. Should be 0 to 3, still the same. And again, we get our function squared as the integrand. Okay, and our pattern continues that we have a different constant, but the same. I bumped that, I don't know if you heard the end, the same integrand. So now we're going to, and I need to also say that this is intended to be isosceles as well. So we need an isosceles right triangle. This time the hypotenuse is going to be on the actual region. So let me see if I can erase this again carefully. So this is now back to our picture. Now here's our representative rectangle again, and this time we're saying that this is the hypotenuse. So as we come out here to get our triangle, this is going to be the right angle that's up here, pointed up in the air. Let me see if I can redraw that over here. So it's going to look something like this. And remember, this is still isosceles, so these are going to be the same length, but our hypotenuse here is going to be on the actual region. That part is going to be on my iPad or your paper as you take notes for this. So our delta volume is again going to be the area of the cross-sectional piece times delta x. So that's still going to be a 1/2 base times height times our delta x. And now on this one, so we have our 1/2. Now the base is going to be, this is our function right there. So that in our case is the 3x minus x squared. Now when we draw a perpendicular down here to get the height, notice that since these were 45-degree angles to start with in our isosceles right triangle, now we have a smaller right triangle here. Since that's 45 degrees, so is this one. So that means that this length must be the same as that length. Now we can see that that's going to be half of our function 3x minus x squared. So that's going to be the same as this length. So our height is that 1/2 3x minus x squared. So let's see if I can go back to the white. So our base is going to be that entire base across here. That's the 3x minus x squared. And our height, we said, is going to be a 1/2 3x minus x squared. And there's our delta x. So that delta volume is, we're going to get a constant of 1/4. And then our function, in this case 3x minus x squared times delta x, and we go to our volume, which is going to be then that integral from 0 to 3 of the 3x minus x squared dx. So those are the most typical kinds of cross sections that you will be asked to find the volumes of, although you never know for sure. They can come up with something else. All right, very good.